Welcome to Pomodoro Joe for Friday, September 1st, 2023. Today we're looking at LeetCode problem 338, counting bits. This is an easy problem. Given an integer, n, return an array answer of length n plus 1, such that for each I from 0 to n, inclusive, answer at index I is the number of ones in the binary representation of I. All right. So this is pretty tricky for an easy problem, but essentially we're given a range. So we're given a single integer that represents a range from 0 up to and including that integer. So up to including n. We need to count all of the ones for each one of those numbers in that range and return that in an array. So for this example, n is 2. So for 0, there are 0 ones because 0 is just represented by 0. For 1, there's 1 1. Because 1 is just represented by 1. And then 2, there's 1, 1 again, because 2 is 1, 0 in binary. All right, so then we'll return 0, 1, 1. Okay, example 2, n is 5. Well, that means we go from 0, 1, 2, 3, 4, and 5 and count those ones. Again, 0 is just represented by 0, so you get 0. 1 is 1. 2 is 1, 0, so you have 1. 3 is 1, 1, so that's 2 ones. 4 is 1, 0, 0, so there's just 1, 1. And 5 is 1, 0, 1, so there are 2 ones. Okay, so this is going to be a little bit tricky, but I think we'll just jump in, put 25 minutes on the Pomodoro timer, and we will get started. So I will start with some result, and this will be an array, and at the end I will return our result. Now I'm going to break this down into some smaller pieces to make it a little bit easier to understand. So first, we'll just go through our for loop. That will give us all the numbers between 0 and n. So for every number between 0 and n, so that's in range n, and we have to do n plus 1 because this range is exclusive, meaning it doesn't include the value itself. So we have to go range of n plus 1 so that we go from 0 to n inclusive. So this should give us all the numbers 0 through n. Next, let's actually create a helper function here. So let's do a ones count. And we'll just assign our ones count to the return value of our ones count function. Or count ones, how about that? Count ones. And we'll pass in our number. So I haven't created this function yet. We'll need to create this function. So we'll have this helper function, count ones, we pass in a number, and it will return the number of ones that are in this binary form of this number. Okay, and then we need to add that number, that ones count, to our result. So our result, then we'll append this ones count, and then we return our result. Okay, so far what we've got, we have an empty list for our current result. Then we have a for loop for every number in the range from 0 up to and including n. So we have to do n plus 1. We will go through and we'll actually call a helper function, count ones, passing in that number. So first we'll call count ones with 0, then we'll call count ones with 1, then count ones with 2, count ones with 3, all the way up to count ones passing in n. That will return the number of ones in the binary representation of this number. Then we'll just store this number in our result. So we'll append this number to our result, this ones count to our result, and at the end we return our result. All right, so let's create our helper function here. We'll define our count ones. And we're going to take some number. I'll just call it num. I'm going to try to keep these a little bit distinct so we don't have confusion about what we're looking at here. Okay, so to count the ones in our num. Now there's a bunch of different ways we could do this. There are some built-in things that Python can do. I'm going to avoid that. I'm going to teach you sort of the computer science learning way to count the number of ones in a binary number. This is the easy way. And it's not easy, but it's easier than some of the more complicated math ways. So for this, we will have some count. And I'll set it to 0, and we'll return the count at the end. So this is our base. We have our count, set it to 0. We'll go through and we'll modify our count, and then we'll return that count at the end. And then that count will get stored in this ones count. Okay, So then for this, we'll actually be doing something called bit masking. So our number, num, is represented in binary by a bunch of bits, 1, 0, 1, 0, 0, etc., etc. So what we'll be doing is we'll be masking out just the least significant bit. So essentially, we want to ignore all of the bits that are not the least significant bit, the rightmost bit. We just want to look at the rightmost bit to find out, what is that? Is that a 0 or a 1? So to do that, we will use a bit mask. Once we figure out if that's a 0 or a 1, we can add that 1 to our count, or we can ignore it if it's a 0. And then we'll shift all of our bits to the right. So our number will shift to the right by 1 bit. And then we'll do it again. And we'll keep doing that until our number is completely shifted to the right and we just have 0 left. So while we have some number, that means while this number is not 0, first thing we'll do is check to see if this is a 1 or a 0. So I could put an if, or I could just add the count. I think I'll just do this. I'll call this the bit. So we're going to take our current number and we are going to mask it with our bit mask. Now for this, I'm just looking at the least significant bit. So our bit mask will just be 1. So 1 is equal to 0, 0, 0, 0, etc., etc., 1. That's what this represents. So if I have a number 1, all of the other numbers in this binary representation of this 1 are zeros, except for the least significant bit, which is a 1. So I'll just make that here. Okay, so it would represent something like this. That would be the binary, the 32-bit binary representation of 1. As you can see, these are all zeros. And so what I'll do here is I will mask this with the bitwise AND operation. So that's a single ampersand. So sometimes in other languages you'll see 2 ampersands next to each other, like this. When you see that, that's a logical AND. That means you're looking at true and false, and you're checking to see if something is true and false, and you're ANDing the booleans together. But a single ampersand is typically a bitwise AND, meaning you're going to take all of these bits and you're going to do a bitwise AND with this number. So that means everything that has a 0 here, when you AND it with 0, so 0 and 0 is a 0. Let's see. You might need to familiarize yourself with truth tables. So truth tables just let you take some bits. So with a truth table, if you have 2 bits, you have a 0 and a 0. Or you can have a 0 and a 1. Or you can have a 1 and a 0. Or you can have a 1 and a 1. So this is a 2-bit truth table. So you have 2 bits, 0 and 0. You have 2 bits, 0 and 1, 1, 0, 1, 1. Now with our AND operator, 2 zeros, when you AND them together, will equal a 0. 0 and 0. Same thing with 1. 0 and 1 is a 0. The 0 like blocks that 1. 1 and 0 is also 0. It's only 1 and 1 where we get another 1 out. So what we're doing here with our bit mask, all of these zeros will essentially block out all of the corresponding zeros in our number. All of those will end up being 0, and then we only look at this last bit here. Now if this last bit is a 0 in our number, that's going to be a 0 and a 1, so we'll get 0 back out. If the number has a 1 in that last bit, then we have a 1 and a 1, and that will give us a 1 back out. So our bit in this case, I guess I'll leave this in the code. So our bit in this case is just our number doing a bitwise AND with our 1. So that's our mask. Okay, and now our count, we can just increase our count by this bit. If this bit was 0, our count doesn't increase. If this bit is 1, then our count does increase. At the end, we return our count. So this is it. This is actually pretty tricky for an easy problem, but it's a great one to learn, especially learning bitwise operations and binary numbers. All right, let's run this, see if we can pass. Oh, I forgot the most important part. Of course this won't pass. All right, so why didn't this pass? Because I forgot the most important part. Once we do our bitwise AND, we actually need to shift our number to the right. So that we use our shift operator. So we say number is equal to the number, and we'll do a right shift, so that's 2 of these little carets. So right shift by 1 bit. So we're going to shift our entire number by 1 bit. And then we'll shift it again, shift it again. At some point, we'll shift out all of the 1s, and we'll just have 0s left, and that will break out of this while loop. Okay, try that one more time. There we go. Now let's submit that. And we pass, and we do terribly. So we only beat 19% for runtime and 66% for, well, 65% for memory. So this is not the best algorithm, but I think it's a good one to learn on. Let's see, I'm actually going to get rid of this. Let's just see if changing some of these will make it any faster. I doubt it. One thing we could do, instead of using this helper function here, we could actually just move this whole thing into this. So let's try that actually. So we still want our count, or maybe I'll set our ones count. Here we go, we'll do this. We'll have our ones count equal to 0, while our number exists, and while that number and 1, then we shift our number and we increment our ones count. Okay, so now we can get rid of this helper function. Now, honestly, I like the helper function. I would recommend you use helper functions where possible, but in this case, I'm just trying to get a little bit of speed, see if this helps. Not at all. So we were at a 19.58 and now we're at 19.89. So it doesn't help at all. It does help us with some memory though. We're at a 94% for memory, so that's pretty good. All right, let's take a jump in here and take a look at what other people are doing. All right, so for this, they've got some early outs. That's pretty smart. If you just have n is equal to 1, you already know what the answer is. Same thing with n0, you know the answer. Now for this, oh, they're doing something very clever here. Now, I'm not going to go explain this because you've already had enough, and frankly, I don't understand it myself. So that's it for me. Hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.